All right, welcome back, everyone. Um, we're going to start covering some new material this week, although obviously we still have an exam coming up this week as well. I guess one of the advantages of being online and asynchronous like this is that we can kind of do both at the same time. Um, so, we're going to head on into the next section. Nothing that we're going to be talking about here will be included on exam 2. Um, and we're going to sort of build off of our successes that we found studying energy. And in particular, energy allowed us a new way of looking at motion instead of having to follow the trajectories of particles. Um, uh, we could sort of take a before and after, or a snapshot here and a snapshot there, a more you know accounting way of thinking about physics. It was certainly simpler. We could just sort of relate the situation at one point to the situation at the other point, um, without having to understand everything that happened in between. Um, and that was very powerful. It allowed us to study some problems that would otherwise be more difficult. But there were a couple of downsides, and the first and most obvious downside was that we lost all sense of direction. Energy is a scalar quantity, um, and therefore we didn't have um, a we had to supply all the directional information. We had to use our physical intuition about the way things moved to fill in the blanks for the arrows, basically, where things were happening and in what direction. Um, and so the question is there a middle ground where we can still use a conserved quantity? We can still do this sort of before and after technique, but can we find a conserved quantity which retains some of that directional or vector information? And the answer is, thankfully, yes. To set this up, let's go back to Newton's second law, which says that the sum of forces is equal to mass times the acceleration, and the acceleration we can write as the time derivative of velocity. Now, if we assume that the mass isn't changing while the force is acting on it, then we can actually then mass is a constant, and we can actually move it inside that derivative, like so. And we can rewrite the sum of forces as being the rate of change of this new quantity, the mass times the velocity. And if we define that new quantity and give it a name, we call it momentum. We give it a symbol, a p, which is also a vector quantity. This vector quantity, the combination of mass times velocity, fills a new space. It's a different way of thinking about this same thing. In particular, velocity tells us how fast something is moving. It's very intuitive, but it misses a piece of the information. So, for instance, if you have a mosquito coming at your head at a meter per second, that's a very different experience than if you have a bowling ball flying at your head at a meter per second. Obviously, the bowling ball is a much more significant event than a mosquito, and we should recognize that significance somehow, and momentum would sort of allow us to do that, because those two events, while the mosquito and the bowling ball have the same speed, obviously the bowling ball has a lot more momentum. It's got a lot more oomph to it. And oomph is sort of a way that you can kind of think about momentum, right? It's the amount of oomph that a moving object might impart to you if it runs into you. It has units. Well, it's a mass times a speed, or mass times velocity, and so it's going to have the units of kilograms times meters per second. And in this case, those units don't have any special name applied to that. We just call it kilogram meters per second. If we then rewrite Newton's second law in terms of this new quantity momentum, what Newton's second law says is that the net force on an object is equal to the time rate of change of its momentum. And the absent forces, if there aren't any unbalanced forces, if the net force on an object is zero, then its momentum will remain constant rather than its velocity, or indeed they are the same thing. That is, momentum is a constant absent forces. So again, this is just a rewriting of Newton's first and second laws with some different terminology. We've applied a different label, we've used a different symbol, but there is a subtle difference here. We're talking about the rate of change of oomph, if you will, being supplied by forces. Well, we've talked about Newton's first law and Newton's second law. What about Newton's third law? Well, Newton's third law is the one that says action and reaction are the same. So that if there's a force of A acting on B, that's going to be this pink vector, the two objects pushing against one another. Object A pushes on object B, and that's our pink force vector. Newton's third law says that if there is a pink force vector of A pushing on B, then there is also a blue force vector in this case of B pushing on A, and that those two vectors have equal magnitude and opposite direction, which we can shorthand here as the vector FAB is equal to minus the vector FBA. Well, if we then take those forces and turn them into the rate of change of momentum, the force of A acting on B, that's all of the net forces acting on B, that's going to be the rate of change of B's momentum, right? The time derivative of B's momentum. And the force of B acting on A, well, that's going to be the rate of change of A's momentum, or the time derivative of A's momentum. And then Newton's third law says that there's a relationship between those two rates of change, and that the time derivative of B's momentum is just the opposite of the time derivative of A's momentum. Now, if we consider the total momentum of the system A and B, right, if we ask ourselves what's happening to the total system of A and B, well, it has a total momentum, which we could get by just adding up the individual, sorry about that, the individual momenta, adding them together, so that the total momentum of our system is just the momentum of A plus the momentum of B. If we then ask ourselves what happens to the total momentum, well, any change felt by B, A would feel exactly the opposite change in momentum, and so this sum of the momentum of A and the momentum of B will remain constant, right? So by Newton's third law, the total momentum of this system is conserved, and that will be true anytime the only forces acting on the system are acting between objects which are part of the system. If the only forces acting on the system are what we would call internal forces, a force from one part of the system acting on another part of the system. Well, Newton's third law will guarantee that that force is accompanied by an equal and opposite reaction force, and therefore that the total momentum of the system will be conserved. We can transfer momentum from A to B or from B to A, but the total momentum of the system of A and B together will always be constant. This is what we call the law of momentum conservation, and herein lies our conserved quantity and our method that we can use to adopt a sort of energy conservation style of thinking about the interaction of objects, but in this case with a vector quantity momentum. And the notice here that this is a vector equation, that the total momentum as a vector must be conserved, and that the total momentum is the vector sum of the momentum of A and the momentum of B, and so on. So we've retained the directionality, the vector-like nature here, but now we can apply it in a sort of before and after context because we have a conserved quantity. All right, well, let's see if we can put this concept to work. So here's an example. It says, astronaut litter bug. A 68.5 kilogram astronaut is doing a repair in space on the orbiting space station. She throws a 2.25 kilogram tool away from her at 3 meters per second relative to the space station. With what speed and in what direction will she begin to move? All right, so as always, step one is we can draw ourselves a picture. Here's our space station, and our astronaut. You can tell it's an astronaut because she's got a backpack. And she starts here with some sort of a tool, say a wrench, and they're just sitting there, presumably at rest relative to the space station. And then, so this is our moment one, or our before moment. And afterwards, here again is our astronaut. She's thrown the tool, and the tool is moving at a speed. Here, the velocity of our tool is 3.20 meters per second relative to the space station. And the question is, how fast is the astronaut moving and in what direction? All right, and we're going to use this concept of momentum conservation, and we're going to look at our system here being the system which includes both the astronaut and the tool, because that's the system where the force is involved. She exerts a force on the tool, it goes away. That force is a force internal to our system only if both the astronaut and the tool are a part of that system. So here's our moment two, and we can say that the momentum, the total momentum of our system at moment one has got to equal the total momentum of our system at moment two. And let's just assume that she starts not at rest relative to the space station, and we'll use that as our frame of reference. If she and the tool are both not moving relative to the space station, then our initial momentum is 0. Right? They're not moving. There's 0 velocity, therefore the total momentum of our system at moment 2 must also be 0. Now the momentum of our system at moment 2, that's going to be the momentum of our astronaut at moment 2, plus the momentum of our tool at moment 2. Well, let's expand those out then, and let's go ahead and say that this is the plus direction, and that therefore is the minus direction. All right, and so the momentum of our astronaut, well, that's just the mass of the astronaut times the velocity of the astronaut at moment 2. And that's a vector quantity, plus the mass of our tool times the velocity of our tool at moment 2, and that's also a vector quantity. We're going to turn these vectors, we'll just call this the plus x direction, and so then we can write these vectors as this is mass of the astronaut times the speed of the astronaut. I'm going to go ahead and drop the subscript 2 here. Well, no, we'll keep it around. Now in the I hat direction, plus the mass of the tool times the speed of the tool at moment 2 in the I hat direction. And the speed of the tool at moment 2 is our 3 meters per second in the positive x direction. So we're solving here. What is it we want to know? We want to know with what speed and what direction should we begin to do. So we need to know, we're looking for this quantity. We want to look for the velocity vector of our astronaut. All right, so this equals 0. So we could move our, let's move the, we'll just move the, we'll move the tool to one side and the astronaut to the other. So the mass of the astronaut times the velocity of the astronaut at moment 2 in the I hat direction must equal minus the mass of the tool times the speed of the tool at moment 2 in the I hat direction. Notice we can go ahead and cancel that I hat directionality, and we'll notice that then the speed of astronaut 2 would just be whatever the value of this, or the speed of this astronaut 2 will be relative to the plus I hat direction. And so v of a at moment 2, speed of the astronaut at moment 2, that's minus the mass of the tool times the velocity of the tool at moment 2, the speed of the tool at moment 2, divided by the mass of the astronaut. So this is minus, our tool has a mass of 2.25 kilograms. Our speed here is 3.2 meters per second. And the mass of our astronaut here is 68.5 kilograms. And so we can take 2.25 times 3.2 divided by 68.5, and our speed of the astronaut is minus 0.11 meters per second. This minus sign here would mean that the velocity vector for the astronaut is minus 0.11 I hat, or 0.11 meters per second in the minus I hat direction. So in other words, she's moving at 0.11 meters per second in the direction opposite to the motion of the tool. Okay? They will have equal and opposite momenta, right? That we could look at this and say that the momentum of the astronaut at moment 2 must be the opposite of the momentum of the tool at moment 2. They're moving in opposite directions with identical masses, or with identical momenta, identical quantities of momenta, but in opposite directions. Since the astronaut has a lot more mass, her speed is a lot smaller than the tool is. All right. Let's ask ourselves a question here. Is momentum conserved when you drop your keys? Or when you drop anything? I don't have keys with me, but I got a pen here. I can ask myself, is momentum conserved when I drop the pen? Well, it's a sort of a silly question, right? Because what's the velocity of the pen up here compared to the velocity of the pen down there? Obviously, the pen's velocity is changing, and so the momentum of the pen isn't conserved. It has a different velocity at different times. But is there a sense, or is there a system or a point of view for which that motion might conserve momentum? And that the answer is yes, there is a system for which letting go of the pen conserves the momentum of the system, and that has to be a system where the force acting on the pen is internal to the system. It's a force between the pen and some other part of the system. Well, what is the nature of the force acting on the pen that causes the pen to accelerate? Well, it's the force of gravity. Where is gravity coming from? Well, in this case, the planet Earth, the entire planet is pulling on the pen. So the Earth exerts a force on the pen, and there's a reaction force of the pen exerting a force on the Earth. And Newton's third law says that those forces have to be equal and opposite. And therefore, the only force acting on this pen is a force between the Earth and the pen. So if we make our system the system of the Earth and the pen, then yes, dropping a pen conserves the total momentum of the system of the Earth and the pen. Now, it doesn't conserve the momentum of the pen itself, just the total momentum of the system of the Earth and the pen. In this particular case, it's a fairly silly thing to worry about, because the measuring the amount of momentum change in the pen, well, that's easy to do. Measuring that same momentum change in something as massive as the Earth, we're never really going to be able to detect that. But in principle, yes, there is a system where you can you can imagine where dropping a pen conserves the total momentum of that system. We just have to make sure that the force involved is internal to the system. In this case, we have to make sure that in this case that would involve the system being the combination of the pen and the planet Earth. All right. So we've talked about we've looked at the concept of forces with respect to this new idea of momentum. What about energy? Well, if kinetic energy can be written as 1/2 mv squared, well, we can rewrite that as 1/2 of mv times v, and mv, well, that's the magnitude of momentum. Right? So that's 1/2 p times v. So momentum times speed gives you 1/2 momentum times speed gives you kinetic energy. And if we multiplied the top, or multiplied by 1 by multiplying top and bottom of a fraction here by mass, then that allows us to take that second speed and turn it into a quantity mv again. So now we would have p squared on the top. That's the square of the magnitude of momentum divided by twice the mass. This is another way of writing down kinetic energy. So we can write down kinetic energy in terms of velocity, but if we're working with momentum, it is often convenient to think about the kinetic energy in terms of momentum, in which case the kinetic energy could be written down as p squared over 2m. So if we go back to our astronaut and wrench problem, our astronaut and tool problem, who has more kinetic energy, the astronaut or the wrench? Well, we said that both astronaut and wrench had to have the same amount of momentum. Right? If we go back and look at our thing over here, we said they have the same magnitude of momentum, right? So that the p squared for the astronaut is going to be p squared for the tool. They have the same magnitude of momentum in different directions, but when you square it and just square the magnitude, we don't notice the directionality anymore. So they both have the same momentum. Which one has the more kinetic energy? Well, the one that has the smaller mass, right? So in this case, the tool will have more kinetic energy than the astronaut does, even though their momenta are split identically. The astronaut will have less kinetic energy and the tool will have more kinetic energy. And this is a thing we'll see often, is that when we're conserving momentum of a system, but changing the speeds or changing the, transferring momentum from one part of the system to another part of the system, objects which have identical momenta but different masses, the smaller your object for a given mass, the more energy that object has in terms of its kinetic energy. All right. Well, let's sort of look here and examine what advantage we might gain from momentum. We talked a little bit about this idea of oomph being sort of wound up in this concept of momentum, but we're still sort of doing very similar kinds of things that we could have done with Newton's law. So the question is, what is it that this business of momentum conservation gets us that would be harder to deal with from the concept of Newton's laws? And the answer is collisions. Now, a collision is what happens when one object runs into another object catastrophically. There's a brief moment where those two objects are interacting, and often, if you actually look at what's going on in such an interaction, it's very, very complicated and messy. So here we have from YouTube a video of somebody hitting a tennis ball hard enough to cause the tennis ball to move at 142 miles an hour after being hit. And it's being filmed here with a super slow motion camera that's doing 6,000 frames per second. So it's taking 6,000 pictures every second. And we can take a look at what does it look like when a tennis ball actually hits the racket. So here we can see, here comes the tennis ball, or the tennis ball is just sort of sitting here. Here comes the racket, and it begins to collide with the tennis ball, and the tennis ball is just pancaking. It's flattening, almost completely flattened, and then it begins to rebound and fly off the strings. If we back up there a little bit, you could see. Let's look at that interaction again. So not only is the tennis ball getting squished, but you can see actually the racket strings themselves are stretching. So things are getting deformed and stretched and sprung out. I mean, if you imagine that both the tennis ball and those racket strings are sort of elastic, kind of like springs, then there's a whole bunch of complicated interaction going on there. And as the ball comes off the racket, you can see it's still deformed. It's in fact ringing kind of like a bell as the various pieces of the ball vibrate against each other, trying to come back to shape. All right, if we wanted to try and capture that interaction with Newton's laws, that would be a huge mess, because the force acting between the ball and the racket is changing super rapidly and is in all sorts of complicated directions. Trying to collect all of that in a sort of moment-by-moment Newton's law perspective to calculate the acceleration, which must also be a hugely strong function of time, changing rapidly, it's going to be very, very difficult to capture the physics of that. But there are parts of this problem that we could capture without knowing all the complicated details of how the racket and the ball interact, if we can sort of boil it down to the momentum that's changed during the interaction with the racket and the ball. Right? We can look at the change of the ball's momentum. Right? It starts basically just hanging there in midair and then is moving at 142 miles an hour. So we could examine the change of the momentum of the ball without having to get into all the nitty-gritty details of exactly how that momentum change happened. So, gotta love apps. All right, so let's sort of investigate how this could come about. Well, collisions are messy, but they're typically short-lived, right? So the idea is collisions don't last very long. While the collision is happening, something hugely complicated is going on. But it's so short that often nothing else of interest is happening in our system during the collision. And so if we could apply a sort of before and after approach, examine the system just immediately before the collision, and then again just immediately after the collision, right? Then if we could just compare those two and use a sort of before and after technique to jump the gap of complicated stuff happening, well, then that would be great. And what we need to do then is have a concept for a work-like quantity, right? Remember, in energy, when we were thinking about energy, work was energy that was being either transferred into our system or transferred out of our system. If something did some work on our system, if the work was positive, then it added energy to the system. If the work was negative, it took energy out of the system. So if we can define a work-like quantity, which is basically the change in the momentum, then we could do that. Well, we can. That work-like quantity is a quantity we call the impulse. Right? And we can write the impulse as the integral of the force over some very short time interval, right? And this integral of the force with respect to time will give us a quantity here, which is that the average force during that interval, during which something complicated is happening, times the time interval that complicated thing is happening. And this quantity, the average force times the time, or the integral of the actual force with respect to time, we call that the impulse. And if you have multiple forces acting on an object, you can create a total impulse by just adding up individual impulses. And again, this is a work-like quantity. Impulse is the rate, or is the change of momentum, just like work is the change of energy of a system. And in that way, we can use this equation here. The impulse is delta P. Impulse is the change of momentum. That's essentially the work energy theorem written in momentum form. So instead of it saying work is the rate of the change of energy, then impulse is the transfer or change of momentum. All right. So if we go back to our tennis question here, and we ask what impulse was delivered to our tennis ball during that serve, well, let's go figure it out. What impulse was delivered to the tennis ball? Well, what happened here was that we had an initial momentum, our before momentum, just zero, right? The ball was just kind of hanging there. If you hit a tennis ball with a perfect serve, you're supposed to hit the tennis ball right at the apex of your toss. You toss the ball up in the air, and just as it's stopping, hanging in the air like that, that's when you hit the ball. All right. So the momentum before the racket hit the tennis ball is zero, and just after the racket hit the tennis ball, well, that's going to be the mass of our tennis ball times the velocity after of our tennis ball. And in this case, the velocity after was 142 miles per hour, or so we've been told, and we can call that in the plus x direction for lack of a better thing, so that the magnitude or the speed of the velocity, or the magnitude of the velocity or the speed just after the ball was struck is 142 miles per hour. So what was the impulse? Well, the impulse is our delta P, and that's the momentum after minus the momentum before. In other words, the change of momentum. And in this case, the momentum before was zero, so our impulse is just the momentum after. And so if we wanted to know the magnitude of that impulse, that's mass of our ball times the speed after. Well, a tennis ball has a speed, or has a mass of 58 grams, or 0.058 kilograms. Our speed was 142 miles per hour. And let's convert miles per hour into meters per second. Well, there's 1,609 meters per mile. And 1 hour is 60 minutes, and 1 minute is 60 seconds. And so the magnitude of our impulse here is 0.058 times 142 times 1,609 divided by 60 and divided by 60 again, or 3.68 kilogram meters per second. Right, so the units of impulse also have to be the units of momentum, just like the units of work were the units of energy, and the units of momentum are kilogram meters per second. So our impulse that was delivered to the tennis ball was 3.68 kilogram meters per second. Technically, our impulse is a vector quantity, so that's 3.68 kilogram meters per second, and in this case, again, in the positive x direction, so I hat, in the same direction that the force, or the velocity was afterwards. All right, well, we can describe that change of momentum, but we can also ask, what was the average force on the tennis ball during that ball and racket interaction? Well, we can also say that the magnitude of impulse is equal to the magnitude of the average force times the amount of time the interaction took. And so if we wanted to know the average force, that's going to be our impulse divided by our time interval. We know the impulse, 3.68 kilogram meters per second. So the question is, well, how long did that interaction take place? Well, let's go back to our video. We can time it because we've been told that this collision is being filmed at 3,000 or 6,000 frames per second. So all we have to do is count the number of frames that the interaction is taking place over. So, not quite there yet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, we'll say 20 frames. It's a nice round number anyway. So we'll say 20 frames was how long that interaction took. So our delta t here is 20 frames. So therefore our force is our 3.68 kilogram meters per second divided by 20 frames. But now we have to convert frames to seconds. And to do that, we're going to use the frame rate. There are 6,000 frames in 1 second. And so now the frames will cancel, and we take our 3.68, divide it by 20, multiply by 6,000, and we find that the average force, or at least the magnitude of the average force, is about 1,100 newtons. That's a fairly significant amount of force. We're used to pounds here. How much is 1,100 newtons? Well, 1 newton is 0.225 pounds. So this is also about 250 or so pounds. So roughly 250 pounds of force on average smashed into that ball. And indeed, at peak, it was probably quite a bit more than 250 pounds of force because we saw that the ball squished entirely and then rebounded. Well, most of that time it wasn't super squished. That would be the moment of maximum force. The force was actually probably a very steep function in time, changing very rapidly. The actual force probably looks something like this as a function of time. Very, very sharp peak or something like that, or it might even be more complicated. Maybe it's, got a couple of jaggy bits on it. What we've done is we've just taken the area under that curve, basically the average force or something like that. We said that it's like an average force multiplied by a length of time. So herein we can begin to see some of the advantages of using a quantity like momentum, a conserved quantity like momentum, or a sort of a before and after approach to dealing with these complicated collisions. All right, so let's try another example. All right, it says, kick the ball. A stationary soccer ball with a mass of 0.86 kilograms is kicked with a constant force of 11 newtons. The player's foot is in contact with the ball for 0.13 seconds. What's the velocity of the ball after contact with the foot of the player? All right. So we have our ball. It has a mass here of 0.86 kilograms, a force of 11 newtons, and a time interval of 0.13 seconds. The impulse or change of momentum, at least the magnitude of it, is going to be the force times this time interval. And it's also going to be the mass of our ball times its final velocity, because its initial momentum was 0, so it's just going to be its final momentum. So we can say that the final velocity then is just the force times delta t divided by our mass, so 11 newtons times 0.13 seconds divided by 0.86 kilograms. So 11 times 0.13 divided by 0.86, 1.7 meters per second is our final speed. And notice, again, we didn't have to figure out any accelerations. We didn't have to dig up any kinematic equations and solve them. We very quickly got to our final answer without any of the intervening steps that we would have had to have done if we wanted to know if we wanted to solve this from a Newton's law perspective. So again, this before and after technique cuts out a lot of the middle ground. We don't learn everything. We don't know, for instance, how fast the ball accelerated, but we can get very quickly to an answer without having to go through a lot of intervening steps. And herein is the advantage of this kind of a way of looking at things. All right, let's do one more example problem here today, and then we'll move on to something else next time. All right, so this one says golf drop. A golf ball of mass 0.16 kilograms is dropped from a height of 2 meters. It interacts with the floor for 0.145 seconds and applies a force of 10.5 newtons to the floor when it collides with it. What's the ball's velocity in meters per second right after it rebounds, and how high in meters will the ball travel upon the rebound? All right. Let's start with a picture. So here's our ball up at moment 1. It's not moving. It is, however, a height of 2 meters above the floor, which is down here. Obviously, the ball is going to start from rest and fall. And we're going to call moment 2 the moment just before it hits the ground. And just before it hits the ground, it's moving with a speed v2, but it's moving in the downward direction. If this is the y-axis, that's the positive y direction is up. It's moving downward at moment 2. At moment 3, sometime later, there's a time delta t here, which is 0.145 seconds between moment 2 and moment 3. At moment 3, it's at the same position. It's still at the ground, but now it's just after rebound, and it's moving upward with some velocity. And then, sometime later, it's come to a different height here. Its maximum height, I'm going to call this h sub 4, because this up here is moment 4 when it comes to a stop at its highest point. Now I should probably draw the velocity 2 vector larger, because as we're going to see here, velocity 2 will be larger in magnitude than velocity 3, and height 4 will be less in size than height 4. I only know that because I've solved this problem. So I'm going to draw those vectors correctly. So we have 4 interesting moments in time, and they're connected in different ways. Like from moment 1 to moment 2 here, what's going on is the ball is falling under the influence of gravity, right? That's not a momentum problem. It's not a particularly good, at least not particularly useful for us to examine this problem from the concept of momentum conservation, because the only system in which momentum is conserved would be the system of the ball and the earth. And bringing the earth into this is just going to needlessly complicate things. So let's not use momentum conservation. But the ball is falling under the influence of gravity. Gravity is a conservative force. So from moment 1 to moment 2, we're going to use energy conservation. Energy will be conserved. We're going to use energy conservation to get from moment 1 to moment 2. From moment 2 to moment 3, our ball doesn't even move. It's on the floor at both cases. But when it hits the floor, we've been told it applies a force. That's the force of the ball on the floor, right? Well, Newton's third law says there's also then going to be a reaction force of the floor pushing on the ball. That's the force of the floor pushing on the ball. They will be equal in magnitude, opposite in direction. So the ball will feel a force for a time delta t, and therefore there will be an impulse driven into our ball. So here we're going to use impulse momentum, right? The impulse is the connecting tissue between moment 2 and moment 3. We can calculate what the impulse applied to the ball was and use that to calculate the change in its momentum. And then from moment 3 to moment 4, now the ball has some initial velocity and it's rising up into the air because that's the direction the velocity is going, but as it does so, gravity is pulling on it. And so again, we have a ball acting under the influence of gravity. So again, we have a conservative force acting on our ball, and we're going to go back to energy conservation again. So we have 4 interesting moments in time, and the 3 connections between those 4 interesting moments are energy conservation in between moment 1 and moment 2, an impulse being applied to our ball between moments 2 and 3, and energy conservation between moment 3 and moment 4. All right. So now that we're armed with this idea, let's go ahead and put it to use. So from moment 1 to moment 2, energy is conserved. We can say that the gravitational potential energy at moment 1 is all going to turn into kinetic energy at moment 2. So the gravitational potential energy at moment 1, that's the mass of our ball, times gh. And the kinetic energy at moment 2, that's 1/2 mv squared, but we could also write it as p squared over 2m. All right, there are 2 ways to write momentum. Let's keep it in the p squared over 2m formalism, and solve for momentum too. All right, so move the m over here. That's going to be 2m squared gh equals p2 squared, or and we should note here, let's then we can solve for the momentum, or the magnitude of the momentum here. Then P2 is going to be the mass times the square root of 2gh, but it's going to be negative because our vector here, it's going to be in the minus j hat direction because our momentum is downward, and that will be important here in just a moment. Right? Because what we want to know is, all right, what's the ball's velocity in meters per second right after it rebounds? Well, that means we need to find velocity 3. So it means we need to get to momentum 3. Momentum 3, right? Well, we can get to that by knowing the impulse from 2 to 3. That impulse is the momentum at moment 3 minus the momentum at moment 2. Right? And again, direction matters. It's also equal to the force times delta t, where the force here is the force acting on the ball. So that's the force of the floor on the ball. In other words, it's our upward directed force. Right? So connecting those two equations, we say that P3 minus P2 is equal to the force of the floor on the ball times that delta t, or in other words, that the momentum at moment 3 is just the force from the floor on the ball, delta t, plus the momentum at moment 2. Sorry about that, lost my microphone. And let's go ahead and expand out those momenta in terms of some velocity, or in terms of their j hat directions. Let's expand all these vectors in terms of their unit vector notation. So that's P3, that's going to be our mass times our velocity at moment 3, or our speed at moment 3, and V3, that's going upwards. So that's in the plus j hat direction. Our force, well, our force is going to be, again, the magnitude of that F force of the ball on the, or force of the floor on the ball, times our delta t, and that's also going to be in the positive j hat direction. And P2 we just set up here is minus m times the square root of 2gh in the j hat direction, right? So P2, that's a downward directed momentum. P3 is an upward directed momentum. And we can get rid of the unit vectors there and divide everything by mass to get a value for the speed at moment 3 here is the magnitude of our force of the ball, or force of the floor on the ball, times our delta t, divided by the mass, minus, and the mass here just cancels the square root of 2gh. And so now we can take Move that up there so you guys can see it. Take this equation and start plugging in numbers. So the magnitude of the speed of velocity 3 here is 10.5 newtons. That's the magnitude of the force. And 0.145 seconds divided by 0.16 kilograms minus the square root of 2 times 9.8 meters per second squared times 2 meters. And if we do some calculations here, 10.5 times 0.145 divide by 0.16, that gives us plus 9.52 meters per second. So that's 9.52 meters per second upward minus 2 times 9.8 times 2, take the square root of that, 6.26 meters per second. That's downward. And so 9.52 minus 6.26 is 3.26 meters per second upward. So the ball's velocity in meters per second upward just after it bounces off the floor is 3.26 meters per second. So we used energy conservation to get from moment 1 to moment 2, energy conservation. We used the impulse-momentum relationship, this one. So the change in momentum is the impulse imparted by the floor on the ball to get from moment 2 to moment 3. We then solved for our speed at moment 3. And then to go from moment 3 to moment 4, we're going to use energy conservation again. In other words, we're going to say that the kinetic energy at moment 3 is the gravitational potential energy at moment 4. And so the kinetic energy at moment 3, that's 1/2 mv3 squared, pardon me, is the gravitational potential energy at moment 4, mg times h sub 4. We can cancel the mass on both sides, and we're solving for h4. So h4 is going to be v3 squared over twice g. So that's our 3.26 meters per second. Square that and divide by twice 9.8 meters per second squared. So square this, divide by 2, divide by 9.8, and we find that h4 is 0.54 meters. Right? So here we had quite a complicated problem where lots of different things were going on, but by breaking this up in sort of a transactional or before and after picture, we were able to take this complicated motion of a ball dropping under the influence of gravity, exerting a force on the floor that caused a reaction force from the floor to exert a force on the ball that caused the ball to accelerate back upward until it had a velocity as it came off the floor. There was some sort of complicated force interaction going on here, but we simplified that complicated force interaction with our impulse-momentum relationship here. And then we can, in turn, have the ball rising back up off the floor. So by breaking it down into these before and after pictures using energy conservation and momentum conservation, or impulse and momentum, we were able to break a relatively complicated motion into 2 or 3 moderately complicated steps. and got without too much difficulty to our answer. All right, so we're going to continue with this next time. We'll start talking about collisions, and then we'll really start to see the power here of approaching the problem from a momentum standpoint.